Hello, this is the lecture for section 4.1, exponential functions. Let's begin with a definition. What's an exponential function? Well, an exponential function can be exponential growth or exponential decay. An exponential growth function is one that grows very quickly. An exponential decay function is one that decreases in quantity. All right, the format for the exponential function is here. F of x equals a times 1 plus r to the x is one function, is one format where a is going to be the initial value in the function, right? And r is going to be the growth rate. Okay, it's a percentage. We would write that as a decimal, right? Now, alternatively, we can use the form f of x equals ab to the x, where a is still the initial growth, but b is a growth factor or a growth multiplier. If we use this second version, b can only be a positive value. And we can also think of b further as being either 1 plus a growth rate, a percentage, or 1 minus if it's an exponential decay, 1 minus that rate. All right, so let's take a look at an example, a couple of examples of exponential models. In the first example here, we have some population that is currently 6,000 members, right? And this population has been increasing by 1.2% each day. Write the exponential model for that population and then use it to estimate that population in 2 weeks. All right, well, the standard form that we want to use is either f of x equals a, some initial value, times 1 plus a rate, 1 minus a rate, or b, wouldn't matter. Let's try it first with this format here. 1 plus a rate, if it's growth, minus if it's decay, and then raised to some power, we'll call that x. All right, so for this population, it's currently 6,000, right? So we could say that f of x is equal, a, my initial value here is going to be 6,000, times 1, and is this growth or decay? This one is increasing, right? So it's going to be 1 plus, and we don't want to say 1.2 here because we want, when we calculate with percentages, it needs to be written as a decimal, right? So we would need to move it over 2 places. So that's going to be 0.012 as a decimal. All right, so 1 plus 0.012, and then raised to some power x, but let's see, we want to know what it is in 2 weeks. We don't, however, want that exponent to be 2, do we? No, because look, the growth rate is per day. So instead of 2 here, we want to say 2 weeks. There's 7 days in a week, right? So it's going to be 2 times 7, or 14 days. All right, raised to the 14th power. All right, let's see, what is that value? Let me grab my calculator here. 6,000 times 1.012 raised to the 14th power. It's going to be 7,090. And you know, it is a decimal. It's going to say 0.5. So, however, the decimal wouldn't really make sense in context here, right? Because it's a population of something. So we need to round up or round down. I would say half of a population member doesn't count. So here I would round down, and I would say 7,090, whatever they are, the population of 7,090. Okay. Here's a second example. A business purchases $125,000 of office furniture, which depreciates. What does that mean? It means it loses value. Okay. It depreciates at a constant rate of 12% each year. All right, write an exponential model for the value of the furniture at some point in the future, right? And then find that residual value 6 years after the purchase. All right, looking at our standard form here, the 125,000 is going to be my initial value. That's going to be my A, right? We're depreciating, right? So this is going to be an exponential decay. The value here is going to be getting smaller instead of larger, right? The rate is 12%. Ooh, so as a decimal, 12% is going to be 0.12, right? I'll fit it, so let me write it over here. Okay, so this function here is going to say my initial value, the 125,000, times, and instead of 1 plus the rate, I want to say 1 minus, because it's a decay rate or a depreciation rate. So 1 minus 0.12. Again, then raised to the x power. X is usually time. In this case, it's years. So I'm going to raise it to the 6th power, right? Because our units match. So I'll put that in my calculator. Let's see what that is. 125,000 times 0.88 raised to the 6th power. It's only going to be worth $58,050. And there's some decimals. And in this case, I can use 2 decimals. I can say 0.51 because it's dollars and cents here, but I wouldn't want to carry this decimal beyond 2. All right, exponential growth model and an exponential decay. All right, what if I only have data and I want to model this data? All right, so say I've got 2 data points, but I know that this data is exponential in nature. All right, and I want to find the formula or find the model that would fit this data. So it's going to pass through these 2 points, -3, 4, and 3, 2. So these are kind of like x and y coordinates, right? I might call that -3 an x1 and that 4 a y1. The 3 might be an x2, and then that 2 would be a y2. All right, so just some coordinates that satisfy this model I want to build. And again, my standard form is going to be, oops, hitting all the wrong things, f of x equals a. And instead of the 1 plus r version here, I'm just going to use b for the base, okay, to the x power. Right? B is going to be either 1 plus some rate or 1 minus some rate. But since I don't care anything about the rate here, it's going to be easier if I just use whatever that value of B is going to be. All right, so what do I know here? Well, I know a couple of things. Let's see. I can substitute in some x and y values into my standard form here. With that first data point, I could say that 4 equals, I don't know the A, I don't know the initial value, and I don't know the B, right? I don't know what the B is, the compounding, what do we call it? Not compounding, but the growth factor or decay factor. That's what I'll call B. I don't know what that is in this case, so let me just leave that as B, but I do know what the X is. It's -3. All right, and now the second one, I can sort of write part of a function here too. I can also say that 2 equals a b to the 3rd power. All right, so I've got 2 partial equations here. Do y'all remember systems of equations? These aren't linear, these are exponential, but I can still use that same concept to solve here. I think, let's see, let me solve this first equation. Looks like it's pretty easy to solve for a, so let me go ahead and do that. Now b to the -3rd power, that's going to be the same thing as 4 times a divided by b to the 3rd power, right? So if I multiply both sides by b to the 3rd power, then I'll have solved this for a, right? So a equals 4 times b to the 3rd power. Now I can substitute this expression for a in terms of b into the second equation that I made, and I'll be able to solve for b. Let's see, my room, so I'll do it up here. So 2 then is going to equal, instead of a, I want to say 4b cubed, or 4b to the 3rd power, times another b to the 3rd power. So I can simplify that. 2 equals 4b to the 3 plus 3, or 6th power. Oops. right? Solving for b, well, let's divide both sides by 4. So then b to the 6th power is going to be 1/2. All right, and then to continue solving, I just want to take the 6th root of both sides, right? Because that'll undo that 6th power. So then b is going to be equal to the 6th root of 1/2, or I could write that as 0.5, 1/2 is 0.5, right? Raised to the 1/6 power, right? That's the same thing as the 6th root of 1/2. So let's put that in the calculator and let's see what that is. That's going to be a decimal, right? Let's see, 0.5 raised to the 1/6 power is there's lots of decimals here. Where do I stop? I want to carry more decimals versus fewer. I want to say it's 0.89, let's say 0.9. Let's carry 4 decimals. I don't want to truncate or round it too soon because then I'll get too far off in my final answer, right? So I can now write my model here. I can now write my model. I don't really know what A is, but since I know what B is, I can't quite write my model yet, but I can almost. I can solve for A. I can find A, right? Now that I know B, I can plug that into this equation over here for A, and I can say that A equals 4 times 0.8909 cubed. My calculator will tell me what that is. It's 0.7071. Yeah, I think I'll just carry 4 decimals on that. So now I do have a model here that I can use, right? My model is going to be f of x equals A, which is 0.7071, times B, which was 0.8909, raised to the x power. All right. Should we try that one again? Or I'm sorry, do another example? I'm just checking my work here. Let's look at this next one. Here we want to find a formula for an exponential function that passes through these 2 points here. Now this one actually might be a little easier because look, for this first point, that kind of looks like the initial value, doesn't it? X, which is usually time, but it's the exponent, is 0, so that makes that the initial value. So that's going to be a little bit easier, right? So we'll just say that 9,000 is the A. Here's another point that I can use to find my model, all right? So my function, my standard form here, is going to be f of x equals AB to the x. I already know A, though. It's 9,000. So let me use that second point, substitute those values in for x and y, and I should be able to solve for B. All right, so we're going to say 72 equals 9,000, B to the 3rd power. All right, solving for B, we have to divide both sides by 9,000 and then take the cubed root. Right? So our B here, it's going to be 72 divided by 9,000 raised to the 1/3 power. That's the same as the cubed root, right? Let's put that in the calculator and see what that is. 72 divided by 9,000. Raise that. That's 0.008. Raise that to the 1/3 power. And we see that B here is going to be 0.2. So here's my model now. F of x equals A. That was our initial value. So it's the 9,000 times B, 0.2 raised to the x power. All right. Let's look at another example. Here we have an investment that's valued at $11,000 in the year 2005. Now, by the year 2018, that investment had grown or appreciated to $14,000. All right. What was the annual growth rate between 2005 and 2018? And we're going to assume that this growth was exponential in nature. Okay, we're going to assume that. So what do we do with this? Years are funny things, right? We usually, in our standard form of an exponential function, the input is usually time, right? It can be AB to the x, or A times 1 plus R to the x, where x, or the input to this function, is usually time. However, we do not want to use a year as an input value to a function in general, because what is a year? It measures the distance from year 0. And very seldom are we going to be in a situation where we want to measure the distance from year 0. So because of that, we usually frame our model such, and we usually say, let time, so we'll say, in this case, time is going to be our x, right? We're going to say let x be the number of years after where we think our model begins. And for this model, since the earliest data that I have is from 2005, I'm going to say it's the number of years after 2005. Okay, so I'm just going to frame my data this way. So that means that in the year 2005, in the year 2005, that means that x is going to be 0. That makes, that's time 0, right? That makes the amount in year 2005, the $11,000, that makes that my initial value. So $11,000 is going to be my A. Okay. So let's see. Let's see. We're only trying to find the investment's value. So I don't have to use this 1 plus R formula. I can use the simpler version and just use the multiplication factor here, right? My growth factor, the B, let it use that version of it. So my model is going to look something like this. F of x, or my future value, it's going to be the initial amount. Since I'm framing my data after 2005, I can call 11,000 my initial amount, right? Then times my growth factor raised to the number of years, or to the x power. All right, so to have a full model here, I need to figure out what my B is. Well, it looks like I have a second set of data that I can use, right? Look, by the year 2018, that data, or that value, had grown to $14,000. So 2018 is going to be 13 years after 2005, right? If I subtract out the 2005, I've got 13 years. So this was going to be my x in 2018. Right, so I can use, and then of course my y, or my f of x, is going to be the 14,000. Right, so I can use this data to write a second version of this equation. I can say that $14,000 equals $11,000 times my growth factor, B, raised to the x power. Well, I know my x, my time, it's 13 years after 0, so raised to the 13 power. Now I can use this data to solve for B. So we're going to divide both sides by the 11,000. Okay, and then we're going to take the 13th root, or, actually, let's do it this way, or we're just going to raise this to the 1 over 13 power, because b to the 13th times 1 over 13th is just b to the first power. So that's how we undo that. All right, so we'll put that in the calculator. figure out what that growth factor is going to be. 14,000 divided by 11,000, okay, raised to the 1/13 power. And the answer here is 1.0, let's see, we'll do 4 decimals again, 187, if we carry 4 decimals. All right, so what is that telling us? What is that telling us about the percentage growth here? This is our growth factor, 1.0187. If I subtract 1 from that, this tells me that my growth percent, let's just write it that way, my growth percent is going to be 1 minus 1.187, which will be 0.0187. As a percentage, move that over, we can see that this is growing at 1.87%. Okay, just an aside. Now, what are we supposed to do with this example? Assume the value continues to grow by that same percentage. What was the investment's value in the year 2022? All right. Well, 2022 is 17 years after our model begins, right? The 2005. So that means that my X here is going to be 17. So I can use my new model I just made and find F of 17. It'd be 11,000, oops, times this growth factor, 1.0187, raised to the 17th power. Okay, put that in my calculator. And I can see that the value in that investment has grown to $15,072.31. All right. So with exponential functions, this base is the growth or decay factor, right? This B is the growth or decay factor. It can always be thought of as 1 plus or 1 minus some percentage, some growth or decay percentage. All right. Let's look at a specific financial example that involves an exponential model. So all loans and investments, they either earn money or they cost money, right? And what they earn or cost is referred to as the interest, all right? And the interest is very seldom simple interest. Simple interest is when it's only calculated once per year and then that money is just paid to you or you just owe that money. Typically, loans and investments, the interest is compounded. What does it mean to compound interest? It means that every period of time, whatever the period of time that's being used, the interest is calculated and then it's added back into the initial amount, right? So if you have an investment and it's earning some rate of interest and you just let it sit there, if it's an annual compounding every year, the bank would compound that interest and add it back into your amount that you've saved. Typically, we see monthly compounding in most financial investments and in most loans, right? So that means every month the bank would compound, or the bank would calculate the interest owed to you for your investment, and they would stick it into your account in there with the money that you'd invested. Then the next year, when they calculate the interest, the next month, when they calculate the interest, they're calculating interest on a larger amount. It would be what you'd originally invested plus the interest from the previous year, so on and so forth. So compound interest is nice for investments because your investment grows faster, right? It's not so good with loans, but you can't avoid it. With loans, the interest is compounded every month and put back in there to what you owe, and you've got to pay back more, right? All right, so here's the formula that's used for compound interest. Some amount at some future time, right, is equal to the initial value, the initial investment or the initial loan, times 1 plus, and this R is the annual percentage rate, okay? Very seldom what you're actually paying or earning, right? And the K, R divided by K, where K is going to be how many times that interest is calculated each year, or the number of compounding periods in 1 year. Okay, so it's going to be 1 plus R over K, right? So if you're compounding monthly, you take that annual interest rate and you divide it by 12. And you only apply 1/12 of that interest. But then we raise that to the K, that compounding period again, times T power, where T is the number of units of time. If it's monthly compounding, it's going to be the number of months. Okay? So typically, compounding either occurs annually, once per year. In that situation, the K is going to be 1. It might be semi-annually, where K is 2. Quarterly, if it's quarterly, K is going to be 4. Monthly, K would be 12 because we compound every month. You don't see this very often, but there might be daily compounding where K would be, what is it, 365, right? 365 days in a year, typically. All right, let's look at an example of using this compound interest formula. So if we have $6,000, it's invested in a bank account at an interest rate of 9% per year. That looks like the R, doesn't it? Of course, when we calculate with it, we need to change that percent to a decimal, so it'll be 0.09. All right, we've got the $6,000 we're investing. That looks like the initial amount, doesn't it? That looks like our A, our initial value. Let's write our formula up here so we have it to look at. The future amount as a function of time is equal to the initial amount times 1 plus the annual rate divided by compounding period times compounding period, raised to the compounding period times the number of years. There's our formula. All right, so we know A, that's 6,000. We know our rate is 0.09. Okay, find the amount in the bank after 5 years if the interest is compounded by these different methods. So 5 years, it looks like that's the T, right? That's the T. And if we're compounding annually, what is K going to be? K is going to be 1 because we just calculate that interest and compound it once per year. So this formula is going to look like this. The future amount in 5 years, or A of 5, it's going to be the initial value, that was 6,000, times 1 plus the rate, that's 0.09, divided by the number of compounding periods. Here it's just 1, right? Raised to the KT power, that's the 1 times, and again, T is the number of years, so it's going to be 1 times 5th power. Right? Put that in our calculator, and after 5 years with annual compounding, we will have $9,231.74. Okay. What do you think? Let's skip semi-annual. You don't see that very often. It doesn't add any value. What do you think would happen if we started compounding this quarterly or monthly? For semi-annual compounding, our K would be 2. For quarterly, our K would be 4. Let's do monthly. For monthly compounding, our K is going to be 12. Look at that. What do you think is going to happen to that when we substitute that 1 with a 12? Right? Well, we're dividing that 9.09 by 12, so this becomes 1 point, a very small number, but we're raising it to a very high power here, right? We're raising it, the power we're raising it to is 12 times 5, or 60. This is where the beauty of exponential functions comes in. When the exponent gets bigger and bigger, even very small amounts, very small growth factors can have a big effect. Let's see what it is. So here we want to find a of 5 again with a different compounding period. All right, our initial amount was $6,000 times 1 plus, here this rate, this annual rate gets divided by 12. Right, and we're going to raise this to the 12 times 5, or 60th power. Let's put that in the calculator and see what it is. 6,000 times 1 plus 0.09 divided by 12. Oops, I did forget a parenthesis. Let me put that in there. And then raising that to the 12 times 5 power. Calculator told me now that this is $9,394.09. So look at that difference there. It's quite a difference. Let's see, 92. Let's see what it is. That's a difference of $162.35. Okay. So over time, even though that rate got watered down quite a bit, what is 0.09 divided by 12? It's only 0.075, right? This was 2 zeros, 1.0075. That's a tiny little growth factor, just a tiny, tiny bit more than 1. But because the exponent was 60, we applied that tiny, tiny, tiny growth factor 60 times, right? And that increased our value, our earnings, increased our earnings by an additional $162. All right. There is another formula for continuous growth. You know, a lot of textbooks present this as a financial application, but it does not exist in the financial world. So I wouldn't call this a financial application, but there is a continuous growth formula that we use extensively, actually, in the science world, most often in the biological sciences. Right? And this formula looks like this. It's A, your initial amount, your starting value. It's principal in finance. Here we would just call it the initial amount or starting amount, times E, the base here, right, or the growth factor here is Euler's number. Right? Euler's number is approximated at 2.71828, and it goes on to 828 forever. Euler's number is actually a ratio, right? Your calculator maintains the integrity of that ratio. So when you use E on your calculator, you're going to get the full benefit of all the decimals. All right. R is your annual growth rate. And then T would be the number of time measured in years or in some other unit. It might be in months or days. It could be just about anything, right? Whatever unit of time. Yeah, so maybe. So let's take a look at an example using the continuous growth formula. Here we have an initial population of 6,000 bacteria. All right, there's our A right away. Let's identify that. That's our A, 6,000 bacteria. Here's our formula again. What do we call it? Something? We said A of T, right? So A, some future amount as a function of time, is equal to the initial amount times Euler's number raised to the, not annual necessarily, but the period of time, the rate over a period of time raised, or times the number of time units. Okay, so for this one, we have an initial population of 6,000 bacteria, and it's growing at a rate of 9% per hour, right? So our R here is 0.09. Our unit of time is hours here instead of years. So find the amount of bacteria after 5 hours, there's our T, if that bacteria grows continuously, right? So our future amount as a function of time, the time here is hours, it's going to be after 5 hours. Okay, the initial value, the 6,000 bacteria, times E raised to the growth rate over that period of time, which is going to be 0.09 times the number of units of time, which in this case was 5. All right, plugging that into our calculator, we have 6,000 times, I'm going to use my e to the x key. This is a little easier instead of having to put a caret and everything to get into the exponent. My exponent is going to be 0.09 times 5, and I find that I have 9,000. After 5 hours, the 6,000 bacteria has grown to 9,409.87 and more. But I don't care about these decimals here because I can't have a portion of a bacteria. So I'm just going to say I only have 9,409 full bacteria at exactly 5 hours. Okay. All right, just a couple more concepts in this unit. Jumping back over to financial applications. If we have an annual percentage yield, what is an annual percentage yield? Well, an annual percentage yield is the actual rate of return on an investment that's being compounded, right? Remember when we were looking at the compound interest up here, the compound interest, we were saying that, you know, R was the annual percentage rate, but it's not actually the rate of growth in the investment, because, you know, you're dividing it by that compounding period, and you're kind of compensating by, you know, raising it to a different power that includes that compounding period. So it's often interesting to know what the actual annual rate is. So that's our annual percentage yield. 1 plus the annual rate published, or the annual interest rate, divided by the number of compounding periods, raised to the number of compounding periods, and then minus 1. All right. So let's look at this example. What would the annual percentage yield, or the actual growth rate, be for a savings account that has an annual percentage rate of 5% compounded monthly? Okay. So here our R is 0.05. Our K for our number of compounding periods is going to be 12. All right. So our formula, it's going to look something like this. The annual percentage yield, right? It's going to be 1 plus R divided by K raised to the K minus 1, which would be, for this situation, 1 plus, that annual rate was 5%, so 0.05, and the compounding period was 12 per year, that's monthly. So 0.05 divided by 12 raised to the 12th power, and then you subtract out that 1. Okay. Put that into my calculator, and I see that the annual percentage yield here is 0.0512, right? Or as a percentage, move that decimal over 2 places, it's 5.12%. Right? So even though, so lenders, they will always publish interest rates, annual interest rates that are lower than what you're actually paying, right? So you might see a car loan that has a 5% interest rate being advertised, but depending how often they compound it, and they probably do monthly, the actual rate will be 5.12%. It's just a little bit higher. Okay, that ends the lecture for section 4.1.